base, which similar talk given by Gaspard Farge, coming from IPGP. He's now a PhD candidate, and he was graduated from IPGP in 2017, right?
Yes.
And he's now a Fulbright visiting student in William Frank School. So he will be talking about how fluid plays a role to the earthquake swarm. So let's welcome Gaspard.
Should we close the door? Okay, thank you so much. I'm very glad to be able to present my work. It's been a few months I've been here, and it's a very nice opportunity to be able to show this to you. So this is work I conduct at IPGP in Paris with Claude Jopard and Nicolas Shapiro, who is working at ISTER and Grenoble. This is mostly work, so this is mostly work for my PhD. Okay, so today I want to talk to you about how fluid transport in geologic plumbing system can trigger and fuel, can shape swarms of seismicity. By swarms, I mean this kind of seismicity. This is the kind of thought I will be showing most of the time when I'm referring to patterns of seismicity. So this is a time series. You have the axis. The x-axis is just the time. Each dot represents an event. And this is the position along the fault that I'm looking at. Here it's the position along dip in the subduction zone, in the Garrow subduction zone. It's a catalog from William that he made a few years back. And what I'm referring to when I say swarm-like seismicity is the fact that you have seismicity, the fault is activated during discrete periods of times, and so the activity lasts for a short bit and then stops. I'm also referring to, so it's a bit broader a term than what swarms are usually used for, because I'm also referring to the fact that the seismicity is intermittent, and that it has characteristics of clustering in time. And it also shows very small migrations. It's not super obvious here, but I will show you several examples. So yes, indeed, I will start by showing you 3 examples of geologic plumbing systems that display this kind of seismicity and describe a bit the mechanism that go into creating the seismicity. All right, so the most common one that you usually see are crustal faults. When fluids are injected in the faults, it may be in a natural fashion because of natural events, or simply because of man-made injection, we often witness swarms that propagate on the fault. Here you have a map view of the Cahuilla fault in Southern California, and you see a time series of the propagation of the swarm. Again, so it's a space-time graph. You see the distance along the fault, in red along dip, and in black along strike. And what's interesting here is that you see that the propagation is actually not at all continuous. You see it happens in several phases. They say 3 phases, I tend to say 4, because you see that it seems to accelerate and then slow down at several points during the propagation of the swarm. The authors have linked this to the propagation of seismicity in a complex system of fluid transport. And you see the few accelerations here on this animation, especially this one right here, where it suddenly propagates a bit further in the fault. They have linked this to a deep injection point and the mass of fluid being propagated slowly invading the permeable material of the fault, but encountering barriers to the flow. And as the flow goes around barriers or breaks them, you see those variability in the rate of seismicity, which can be directly linked to the pressure at each zone, at each point on the fault. And so it's quite obvious that the architecture of this permeable network then shapes how the swarm is going to look like in space and time. The next system I want to talk to you about that exhibits that kind of seismicity is the first example that I took, and it's going to be actually the main focus of the rest of the talk. after the next example. So I'm going to talk about tremor. Here, the example is taken in the gyro subduction zone. And by tremor, I mean I will use tremor as a broad term, just simply meaning the accumulation of small sources, small sources that sometimes are called LFEs. So we see here that tremor is located along the plate interface, and when we look at its activity along the plate interface, so this is the distance along dip, you see a very active patch down dip, which corresponds to this patch, and a less active patch up dip. And you see that it's activated in large swarms that seem to have a lot of structure when you go down at smaller scale. And you see the same patterns of clustering and migrations, So this intermittence, its presence is present at longer and shorter time scales. And that's an interesting feature of this kind of seismicity that we might want to understand further. So usually tremor bursts are thought to be generated during transients of slip and high fluid pressure on the folds in what are called fault valve mechanisms. Fault valve mechanisms are a way to understand a coupling between slip, permeability, and pore pressure. And so I will show you a little schematic of what it looks like, and you can follow exactly the evolution of pressure and permeability in this small graph. The first stage is a phase of loading. The permeability on the fault interface is closed, and free fluid is produced by dehydration reactions in the fault zone, and the pressure will rise in this closed zone. So we have a first phase of loading. A second phase will be the release of pore pressure as slip nucleates. And as slip nucleates is going to propagate along the fault. And in the fault valve mechanism intervenes here because there will be a creation of permeability, which allows the fluid to propagate and slowly diffuse away. As the fluid diffuses away, permeability closes, it heals, and the cycle can begin again. And so you have cycles of accumulation of pressure and release in the fault interface. And so this is not exactly this is not only a conceptual model. It has been observed in various different ways through seismic imaging. You see the BPDS ratio vary during the time when there are episodic tremor and slip on the fault zone, and other gravitational signals can be associated. The last system I want to talk to you about that exhibits this kind of seismicity is our volcanic plumbing systems. Here I'm going to take the example of the Klyoshevskoye volcanic group in Kamchatka, which is a huge cluster of volcanoes. You see you have 6 active volcanoes in this region. And when we look at them along this strong sect, in this image right here, we see a very active system in terms of seismicity. Looking at this plot, you will see that the activity in depth shows this characteristic intermittence. And this is maybe less surprising to many of you, but in the exact same way as the other systems, it is linked to the activity of the fluid transport system. When there are active seismicity is also linked to the gassing of the system or even to eruptions. There is an eruption right after this, the end of the talk, but that's the total duration of the data that we have here. And when we look into one of the patches, one of the swarms of events that we see on the plot, we see the same characteristics of intermittence and those very fast migrations. The interesting thing about those migrations is that they're too fast to be some kind of movement of fluid. So it's not the actual, it seems unlikely that it is the actual movement of the fluid in the system. And it might be easier to relate it to propagation of perturbations of the system. So it might be pressure perturbations or flow perturbations. And those are the ones that we actually talked about in the previous examples too. So in the magmatic system too, we see that fluid is going to propagate from a deep source towards the surface in a quite complex system where melt and a crystalline fraction are intermingled and they dynamic, and there is dynamic separation of them. And sometimes there can be a seal, a permeable, less permeable seal that breaks and can create those kind of events where there is a sudden impulse of low viscosity fluid that make the medium vibrate, and that can create those kinds of tremor or long-period seismicity. Okay, is it okay if I I forgot about it until I started to choke. Okay. Okay, so in each of those three systems, we saw that the fluid pressure transients that result from the activity and from the dynamics of the fluid transport system can be very much linked to the seismic activity and to its spatiotemporal patterns. And in this talk, I'm going to try and concentrate essentially on how those fluid pressure transients and flow transients appear in this in these fluid transport systems, and in a more general manner. I've shown you some examples. I want to get at a more conceptual view of these events that can help us think about the dynamics of fluid transport system. And the actual question, so that we are able to compare and to understand how patterns are created, we want to know how they will shape intermittence and migration of seismicity. Those will be the main patterns we're interested in. So how do you create fluid pressure and flow transients? The first way to do it is to change the source of the fluid in the system. But that will be simply pushing the problem a bit further, because you want to know why there are source variations in the first place. So we will just assume in the next, in our models, that source flux variations are going to be constant. Instead, we're going to focus on transport properties variations. You understand that with a constant flux and variable transport properties, fluid pressure and flow transients will emerge. And in order so that we have a simple system that produce, without the help of any outside mechanism that produce those pressure and flow transients, we will have some kind of coupling there between the transport properties and the fluid pressure and flow in our system. And that should give us some kind of dynamic behavior, and maybe patterns will emerge from that. So yes, we will design a fluid pressure diffusion system with heterogeneous and dynamical permeability. So as I told you before, I'm going to focus essentially on tremor and subduction zones and as an example, but hopefully we can use the framework to understand seismicity in other systems. So let's look at what the tremor source region looks like and how fluids are transported through this region. This is a picture from a review of the geology of the episodic tremor and slip region. I like it a lot, but there's a lot of information and I won't use it all. All I want you to see is that this is a picture of the subduction zone interface. You can see in red. You see a deep, the slab that plunges underneath, and you can see the oceanic, the continental mantle and crust overlaying. Tremor is located in this region, which is also a region which is quite complex. There's a lot of underplating going on. It's extremely active, and in terms of fluid transport. And you can see it because in, say, different kind of geophysical imaging, we locate a zone of near lithostatic pressure in this region. So where do the fluids come from? The fluids come from the dehydration of this oceanic plate. And as they rise due to their buoyancy, they're going to try and rise through the mantle wedge, through the overriding plate. But the permeability is actually much higher along the fault because of the fracturing. So there's going to be a channeling mechanism that is active in this so there is a channeling of fluid along the plate interface. And you can imagine that it's also very heterogeneous along this plane, and that each the channeling is also active in this dimension, and you see the fluid channels in in channels actually, and we are going to focus on one of those channels when building our model. It's going to be a bit later because in this view, so permeability is quite heterogeneous, but we don't see exactly how. We don't have strong evidence from the geology that there are pressure transients. We actually see it. We didn't. Okay. We actually see it from different samples of paleo subduction across the world. So this is in Iran. This is in California, and you see evidence for very strong hydrofracturation in the fault interface, which hints at very variable and very variable transport properties and fluid pressure in the zone. And these have been linked, so they're in the exact source region as tremor. And so when you think about the same mechanism, the same fault valve mechanism, our hypothesis is that they are linked with tremor in the subduction zone, with the generation and propagation of tremor in the subduction zone. Because of their scale, we are also, we make the hypothesis that they are also linked with the generation of individual sources. That is, during the generation of an individual source, you will have that kind of pressure, rapid pressure transient in the source interface. We have reason to believe that from the source characteristics of LFEs, of those individual tremor sources, we have reason to believe that it is the case. So if we look, for instance, at the scaling between their moment and their magnitude, so this is a plot of their moment magnitude against corner frequency of the event. And we are going to talk about, we're going to assume that the duration of each of those events is proportional to the inverse of the corner frequency. In purple here, you see the self-similarity scaling that most earthquakes seem to follow. And when you measure, when we measured the source characteristic of the LFEs in the Garo subduction zone, we see that first of all, they seem to have quite a lower frequency, which is their characteristics, their typical characteristics. And also that they align on a very different scaling. We see that it's quite a different exponent, very low exponent, but within the uncertainty, we can actually say that LFE duration, or corner frequency in this case, is independent of their magnitude. So this means that you have sources that can be of, for instance, of the same size and producing different amplitudes of waves. Another way to see different slips, if you think about them in the classical way, in a classical earthquake way. Another way of thinking about them is thinking that they're linked with fast pressure transients in the source, around the source region. So that's a way of linking them with the catastrophic fracturation events that we see, and we see that in this case, there is flow that pushes against the low permeability barrier. When this barrier breaks, the pressure transients will diffuse and it will not depend on the amplitude actually of the event. So it will only depend on it's proportional with the inverse of diffusivity of the fault zone, which might explain why we see this constant 2 to 3 hertz duration frequency with those events. Okay, so let's sum up a bit the characteristics that we want to have in our system so that it reflects the tremor source region. The first thing that we want to have is a permeable system that can transport the fluid. So our system is going to be composed of a 1D permeable channel in which fluid saturated with fluid, so that we can define a flux and a pressure for the fluid at each point of this channel. It has a permeability K, and that will be the main parameter describing the transport properties. It's fed with a constant flux that represents the metamorphic flux going into the subduction interface. And it's only fed with a constant flux down dip. So we simplify the fact that there are actually fluid sources along the whole channel. At its output, we see that we have a constant pressure, and you can think of this as the channel being connected to a very permeable fault system, for instance, in an accretionary prism or fault network, continental fault network. So in this system, you can define a hydrolink conductivity using the Darcy law. So the higher the permeability, the easier it is for the fluid to flow, and you will get a higher flux Q you will get a higher flux when you impose a larger differential of pressure across the system. And each element of the channel will be able to store a bit more fluid as pressure rises and dilates the pore. So when you combine each of those characteristics of the system, you get a diffusion behavior for pore pressure. So pore pressure will circulate in the system in a diffusive manner, and that's going to be the equation that we solve. Right now, there is no heterogeneity, no variability, so the pore pressure will just reach an equilibrium in the permanent regime. So what we're going to do, we're going to impose a binary description of this of the heterogeneity of permeability in small barriers, as I was talking to you about in the previous parts of the talks. Still, we don't have any variability. We can change our diffusive equation. That's going to be the equation that we solve. We see that the diffusivity is now variable in space, and but we don't have a time variable diffusivity. So I'm going to describe the processes we think can be at play to explain how permeability is variable in time. So this is a schematics of the plate interface, and you see slab and overriding plate. The fault zone is composed of a thin matrix and large matrix lenses. And so the fluid is going to circulate. And in some regions, the flow is going to be compressed, and the heterogeneity of permeability will create thinner pore throats and can force, and in a system where particles are transported, it can lead to clogging of the system in those parts. So this is not a behavior that has been reported many times on faults, but it has been seen in the lab. It has been seen on the oil reservoirs. We see clogging of the permeable system due to sedimentation of particles that are transported by the fluid. Here it can be cataclasis fines, or it can be colloids that suddenly stick to the walls. But in the end, what it will do is that some segments will suddenly clog, and the pressure will start to rise just before then, stimulated by the impulse flux. But they're going to be, the fact that they're able to clog means that they will also be able to unclog, and a valve behavior can emerge of this kind of system, which has been observed in the lab or in numerical simulations. So let's describe it at the pore scale. What's going to happen is an accumulation of grain in a pore throat. The pressure is going to rise across the difference of pressure is going to rise across this clog, and so you have the same loading phase as in the fold valve mechanism. Permeability is closed. The delta of pressure rises. When it's high enough, the pore will unclog, and you will see a strong pressure transients travel and die off, diffuse a bit further away from the clog. But it will allow the delta of pressure to drop, and the permeability is now open. As the permeability is now open. As the flux diminishes, the particles are able to deposit, and the permeability can heel closed in a clogging mechanism. So here it is. That's going to be the conceptual mechanism that we want to input in each of those segments, each of those various segments. Yes.
Sorry, those particles are sediment particles. What are the particles?
They're particles that are carried by the flow. So you can either think of them as particles that come from this unclogging and are going to clog another flow experiment, another pore throat. And what we think they may be is cataclasis, so fines from the cataclastic processes, or colloids that are transported in those very rich fluids that circulate in the fault zone. And they can be extremely sensitive. So the creation of those colloids can be extremely sensitive to the variations of pressure. So if you have a drop in pressure, you can suddenly have nucleation of those fines in the system. But it's still a toy model, so it's a bit remote from that for now. It's a way to understand this further. So the way we really input this behavior in our system is that we define small segments that can switch from a low permeability to a higher permeability, which is actually the background permeability of our system, in a valve-like manner. That is, during a loading phase, the permeability is closed, and the delta of pressure will slowly rise until it reaches a critical value, at which the valve will instantaneously open, and so it will jump to its high permeability. And then the delta of pressure across the valve will slowly diminish as the valve is open and reach a critical delta P that allows it to close. It corresponds to a critical flux that allows particles to deposit in this system. And so as it clogs, it reaches this closed permeability again, and the cycle continues. If we look at exactly at the time series of delta P across this valve, you see you have loading phases and unloading phases, and quite brutal pressure transients when the valve opens. So we have those pressure transients, but we don't have yet a more explicit link to seismicity in this system. The way we're going to input it is through, okay, so this is just a simple slide to tell you that the dynamics of the mush, of the magmatic mush, can be quite similar actually to what I described you just before. I won't spend too much on this. So now to describe, I'm going to describe the link between the unclogging of the pores and the generation of seismic events. In itself, the delta of pressure, the variation of pressure across these pores, as it's transmitted to the elastic matrix, can generate seismic waves because of the very variable force that's exerted on the porous matrix. And we see that this kind of pressure transients, its duration is also inversely proportional to the diffusivity of the medium, which is quite similar to the characteristics that we measured for LFPs. It also has in subduction zone a similar focal mechanism, focal radiation patterns as double couple. So it could be compatible with observations we have of them. I can talk more about this later. However, it's also compatible with different kinds of sources because we see we have a high pressure anomaly right before the clog that can trigger with a small seismic slip in this region, and that could also open this clog in a full valve manner. But we didn't include this kind of mechanism here. Or the very strong flux transients that we have could generate waves in the system. Okay, so now we are going to couple each valve opening will be considered an event in our system. And after this quite long description of our model, I'm going to try and sum it up quite quickly so that you get how it's going to be. So it's a channel with valves that are distributed across it. We have an input flux, which is constant, a fixed output pressure in our channel. What we solve in our system is the diffusion equation with variable diffusivity. And we add this valve mechanism in each of those segments. That allows us to couple permeability variations with fluid pressure transients. And the last slide I show you tells you that as these react to each other, seismic activity is produced. And the interesting part about this seismic activity is that it's triggered by the fluid pressure transients, but as it's coupled with, as it's directly linked to permeability variations, it also influences the pressure field. And that will lead to interactions between sources because they are, for this reason, for this exact reason. I'm going to develop this in a bit more. But now, as we look into the results, the main questions we want to ask are what kind of patterns emerge and which conditions of the system shape those patterns. So the first thing that I can show you is that I can show you how valves interact with each other. So this is a system where we have the position along the channel, 3 valves, V1, V2, and V3. V2 is going to open, and V1 and V3, we're going to see how they react. They're not able to open in the system. And you see the green line is the pole pressure in this system, and the pole pressure that you see is high at the input is low and low at the output. And so when the middle valve open, you see a strong pressure transient that re-equilibrates the pressure around it. And so more fluid is going to push on the update valve. And so you see that its delta P is going to rise. And on the contrary, fluid is going to be pulled away from the down-dip valve, and the same the delta P anomaly will travel to it. So we have a system in which a valve that opens can trigger cascades of opening valves because of this positive delta P that travels through the systems. And those cascades of opening valves, we consider that they are cascades of events in our system. And so that they are similar to those very fast migrations that we can see in tremor. So when we take a simulation where we input 29 valves that are evenly spaced, we wait for a permanent regime to start. We see patterns we see those cascades extremely well. It's a very simple system. So the activities are actually mainly composed of these bursts of cascades and a few events that are isolated from time to time. Each of those bursts is indeed coupled with the opening of a valve. And so you see that it's coupled with a pulse of fluid that travels through the system. And when we look at the output of the system, we see that actually the most part of the flux is transported by these pulses through the system. So we've created a system that transports fluids in a very unsteady manner, and the activity that is produced can be used to track how it's going through the system. So I'm going to show you now the more complex patterns. We are going to create a more complex distribution of valves in the system in order to force them to interact with each other. And we're going to look at exactly how they interact, what kind of patterns they create. So this is a simulation with this system. I forgot to put the boundary condition, but they're the same as usual, a constant input flux and a constant output pressure. And we see that we have swarms of events that appear at different time scales. We see clustering at different time scales. We see those elementary cascades that appear in more complex within the bursts, and that seem to build up into those larger propagations of events along the fault. If we zoom out a little, we see that this swarm activity composed of clusters of activity on the long term, and a permanent clustered activity is sustained. So I'm gonna show you another simulation. So it's with the same system but a different flux, and we see that different kinds of patterns emerge. We see the same clustering events. We see the same small cascades, same larger scale migrations, but other patterns of migration can also emerge. We're not sure exactly how, why this difference is for now, but I thought it was interesting to show that kind of pattern. Yes.
Sorry. So the migration speed here is roughly the pressure diffusion speed.
No, it's much faster.
It's much faster.
Yeah. It's a good question. I don't have an answer, definite answer yet, but I think it could be due to the fact that so it's hard to define a diffusive speed. That's the first thing. And when the system is close, I'll talk a bit more about this, but it's close to being completely closed, a very small variation. Exactly. And so when it's close to critical point, we're going to see those patterns emerge. I hope I'll have time to come back to it.
It's not, the speed is not the same as the speed of the diffusivity, but is it the speed of the E wave in the matrix, you
think? This is the speed of the P waves. So it would not be in the matrix. It might be in the fluid, but there's no compressibility that is explicitly modeled in the system that well. So I'm not sure. I don't think it is. I don't think it would be related in this way.
Could I see it as
It's very similar actually to pulses of fluid to solitary waves that emerge in diffusive systems where you have permeability that reacts in a less binary manner to fluid pressure. Or you can think of a tube that deforms when there is a sudden high pressure. And so you have solitary waves that propagate. But I would not think that this is exactly the P wave into this medium. Yes.
So how do we compare this to migration?
So the migration, I'll show you some slides afterwards. It's kind of hard to stick one with the other because of the range of permeability that we can use, the range of diffusivity that we can use. There are 6 to 10 orders of the magnitude that we measure in the field or remotely. And we get also very variable speeds and duration of these bursts, duration of the characteristic timescales of the clustering. So it's not it's not an easy task. It's not an easy task. Okay, just this slide to show you that the behavior the valves can synchronize even more, and a periodic behavior can emerge in some cases. Okay. When we look at this kind of periodic behavior, we know that it's linked to the openness of the system, and that we see that it's linked in this very obvious manner. And so we understand that we will see pulses of pressure as each time the system opens, but also that the pressure across the system will drop each time the permeability opens. And if you remember the valve mechanism that I showed you, we see that when we compare the permeability and the pore pressure, and we put it in we can transform it in a way that the loading, the same hysterical cycle appears as for a single valve on the scale of the whole system. So what we think that it means is that large-scale valving emerges from a system where valves are extremely have very strong interactions. And this is quite interesting because you see that we input a small-scale mechanism of valving, and based on observations in the field that can tell us that it's happening on a meter scale, and we get mechanisms that happens on 1 order of magnitude larger, and so that it can be compared to the larger fold valving mechanisms that are observed at the scale of the subduction zones. So this is for comparison. You see it's exactly the same. Okay. I've talked a lot, but I'd like to show you how rapidly how the flux controls activity, and then I think I'll leave this here. You can understand that when the flux is very low, it's not going to be able to push the valve open, and so all valves are going to stay closed because the delta P across them is low enough that they cannot unclog. Above a certain value of the flux, so valves are going to be able to open, but the flux that we impose to the system are not going to let them close in the end. So after a transient of activity of the system, we see that all valves are going to stay open. However, in between, the value of the flux allows the valve, a closed valve to open, but then an open valve to close. And so cycles of opening and closing happen at each valve, which create a sustained activity in the permanent region. And you can notice that it doesn't look at all like the activity I showed you before. That is because the activity I showed you before, which shows those migratory behavior and swarm behavior, happen closer to those critical values of the flux when the system is extremely sensible to small variations, because valves have time to go closer to their to the critical value while staying at equilibrium. And so you see those behaviors emerge. And finally, as I repeated, the system, so you see that the system is going to stay closed. Excuse me. And you see that through this domain where valves open and close, the permeability, the average permeability of the system is going to slowly rise and be more and more open. And the last thing I want you to notice is that in this case, it's kind of hard to see. I should not have put that light, but you see in the very light, there's the activity behind. And you see that there's a positive correlation between activity and opening of the system. However, when the flux is very high, the system is mostly open. And a small perturbation of the system will mean that valves will suddenly close and impede the flux. And the activity this time, each peak of activity will be correlated to the moments where the system closed. And that's quite different from the full valving picture that we have most of the time. This can be called episodic fault clogging if we want to give it a name. And I thought this was an interesting behavior to note when the flux that is forced into the system is quite high. And in the end, we can say that this could help. This is a framework rather than a direct model that could help model how minute seismicity on the faults or in volcanoes could give us an information of how connected the system is, and so how close to an eruption it is, how close to a change in the magma in the eruption it is, or how close the normal stresses are to triggering a bigger earthquakes. I'm going to skip all those ambitious and let you on this take-home message. I think it's important to note that the systems create intermittence and migrations of seismicity, which are sustained in time, but with a constant source. And it's just the simple fluid transport processes that are dynamic, which can create them. Thank you very much.
Thank you, Gaspard. Do we have any questions?
Yes.
I have two questions.
Okay.
One is, you introduced this result about the constant duration relativity. So something you could tell us something about what controls the duration of individual events in your model and why it would be constant?
Yes.
And then maybe I'll wait enough to
Sure. So if we define, once again, I like transparency, and so we don't see anything. there is here we define a valve with a constant width, and we can and so our system is one-dimensional, but we can imagine that we have it can be thought of as a cylinder, and so the valve is actually a disc, not really a disc, it's actually a very thin cylinder. So we can define an area of the force. And the force that is exerted upon this valve is dependent on this area and the delta P that is subject to this valve. And so the variation of this force, which will give us the waves, is actually controlled by the variation of pressure, but not by its amplitude. So the amplitude just comes here, but the characteristic duration of this event is actually controlled by the size of the channel in this area and the diffusivity of this channel. I'm not sure it was clear enough for.
Yeah, absolutely. So the follow-up question then is, are there reasons to believe that the area in this case A would be so uniform along the fault, but even across different fault systems that produces in duration?
I guess not. It's hard to. So what the observations would mean in this framework is that it would be the case for a given fault zone, and that the spread could be represented in the spread of those properties of the diffusivity of the area of the channel. And if there was, but the data that we have from Mexico are also very different in terms of magnitude and frequency, a bit less from the data that are measured in other subduction zones. So I guess it could mean that there are also different properties. But it is all in this framework, and more work is needed on the observations as well on this on how exactly this mechanism translates to seismic waves in order to understand what it means exactly. Okay. Yes.
Yeah, I had a couple of questions. One's just actually a quick clarification. Can you remind me what the criterion was for the valve opening? It was the delta P.
It was a delta P. So,
because that seems to be a controlling factor in these propagations.
Oh yeah, yeah. It is. It is very much so. So that's the exact way I include it into the code. Is really when the valve explodes, it has a low permeability. Delta P is going to rise until it either reaches an equilibrium and the valve will stay open if the flux is very low, or if the flux is high enough, the delta P the actual delta P across the valve will reach a critical value.
Yeah, what's that critical value?
So everything is, maybe you've noticed that everything is out of scale, and so it's arbitrary in this way.
But it is some fixed value. It's not just arbitrarily opening and closing.
Yes, it's a fixed value. It's a fixed value that I attribute to all the valves.
Okay. And the second question was, I was thinking much the same about the propagation rate compared to the realistic scenarios.
Mm-hmm.
And as you just mentioned, a lot of the model is scaled and normalized. Yeah. It seemed quite clear from some of your diagrams what the normalizing constant was for the length.
Yes.
It was just, your conduit 0 to 1,
yep.
Which I can imagine could be scaled up. What was the time normalizing?
The time normalizing.
Everything was time scaled.
The time normalizing was, I'm not sure what I'm looking for here. The time normalizing was the diffusive time in the open system. So diffusive time we define as the length squared divided by the diffusivity. So the characteristic length that we input in our system, and the diffusivity that we input based on the parameters. So we linked. Okay.
So can that be used to scale up to produce a quick estimate of what the propagation speed of these valve openings would be compared to
Yes,
say the real world.
I promised that to Katya also.
Yeah, I had the same question.
Okay, so if we try to do it for the tremor bursts in Mexico, what we'll do is we input the actual length of the tremor channel, and we're going to try to scale to fit these recurrence time between this characteristic recurrence time between each of the tremor bursts that are observed, and their duration also to the duration of our system. And so when I say fit, I just tweaked parameters in order to see what can be doing this. And we see with a quite high diffusivity, but that has been measured with, usually when we measure diffusivity with propagation of seismicity, we get extremely high values compared to what we get in the lab, and high values of permeability that are related to it. We get an input flux, and we get an input flux that can be 10 times the dehydration flux. And that's not absurd, even though it seems like it's like 10 times bigger because of this channeling property of the system. If you imagine that there's a diffusion flux, there's a dehydration flux, which is along the whole fault interface, it's channeled, it can be channeled along 1/10 of the width. Okay, and this will get us, using those values, we get quite similar durations. We get durations of 2 months and 11 days for this simulation. And also we get velocities that are quite coherent. But it's in this simulation, which corresponds to a high flux in which the system is mostly open and closes periodically. And so I did it because I wanted to, but the thing is that those parameters, there's such a, you can tweak them so easily because of the range of permeability that are acceptable, mainly, that it's hard to do. So it's hard to figure out at which scale this could be. Should this be the total length of the system? Should it be a patch of tremor in which those processes are active? That's the question. So, yes. Yes, Katja.
You haven't very thickness, right?
Of the valves?
Along your channel.
So by thickness, you mean the thickness of the valves?
The thickness of the zone that has higher probability to start with, and then diffuses to the background.
So, okay. I'm not sure I see what you mean. The thickness.
Well, the disc has the area.
The width of the.
So you mean this?
Yes.
No, we haven't varied. So in all the systems, I mean, I have varied it. It's what it plays on is the critical flux that allows opening or closing. So it's related because we impose a critical flux. So this is going to be our critical, our control variable anyway. And above a certain flux, the valve is going to open because the delta of pressure will be large enough. But it will be based on a given width of the valve and a given permeability when the valve is closed. So it will actually be reflected in the what is the critical flux for valves to open.
And it doesn't affect the generation
of the seismic events. It does, yeah. And also it might play a role in how quickly the pressure can diffuse through these valves. But for all simulations that I've shown you here, and most of the cases that we are concentrated on, we have a closed permeability which is between 20 and 50 times lower. So you can basically think of it as completely closed. There's nothing that can circulate through the valve in this amount of time. It's just a way to stop the flux in a more physical manner. Yes, Malcolm.
First of all, it's a really interesting talk. I feel like I learned a lot. This goes back to Artie's question about the P wave. You're using the diffusion equation to model your system, which can't incorporate wave physics. Correct me if I'm misunderstanding something. And if the valve opening is primarily just a function of the pressure perturbations, I would think that propagating waves would be pretty important. So do you have either plans to incorporate that into future models? Can you justify neglecting it? How big of a factor is wave propagation, elastic wave propagation?
I
or
haven't.
pressure waves there?
It's. I mean, it's a very good question. I haven't really thought about it. I can try and think about why. So in a diffusive system, I think the propagating wave within the fluid will very quickly die off because of the friction of the pore system. That's why you get the diffusive perm system instead of of wave propagation in the system. However, it could be transmitted, especially during the opening, it could be transmitted to the matrix. And so this wave could actually influence fluid elsewhere. And that's not, and that would actually be very possible. We see that tremor is actually triggered by passing seismic wave that must change the dynamic stresses, so I guess the pressure in there.
Maybe a kind
Yes.
of related technical question, very technical question. What software are you using? Is it easy to incorporate new physics into is it like a finite difference that you could?
It's a finite difference scheme that I built,
You wrote by hand?
Yeah, that I wrote. But so yeah, that kind of physics, I mean, yes, I'm not exactly sure what it would look like if that was an obvious from my answers, but yeah. But it is definitely a very strong characteristic of tremor that it is triggered by small dynamic stresses. So it is indeed important. I'm going to try and think.
But how important? That's a good answer.
Chingy? Whoever, Chingy, you want to?
Thank you for the priority. I do have some practical and quick question. First, regarding the LPs, how do you define the corner frequency, the duration, and what is the magnitude range of LPs for your data? And the second, based on your model, your well model, except that, maybe I already asked that question after. And is there any time delay between the total pressure change and the proportion of open faults? Do you observe any change in your data in Mexico, the migration rate? Do they change before or after some bigger scale as usual?
Okay. I'm going to answer the second question first. I'm not aware of any changes of migration speeds or clustering or after big earthquakes in Mexico. Sorry?
We've never looked at that. Yeah. But it's a fair point. It's just a pain in the butt to define what a migration is.
It's quite hard actually, because you saw that it depends, it completely depends on the scale you're looking at. Small migrations are fast, big migrations are much slower. And so it's really hard to define. And it's also hard to detect. And you really have to go by hand and say, okay, this is the migration, because it's a very noisy data set. And so to answer your question about how we define corner frequency.
Yeah.
Okay, so in this paper we have two ways of defining it. Either we use the peak, the maximum of the maximum of the spectrum of an LFE in a time window centered on the S waves, the 5-second time window. And we look at the maximum between 1 and 8 hertz. And so in the velocity, in the spectrum of the velocity. This is not that, because the method I'm telling you about gives bigger spreads, but not much variation in the scaling. This is the mean of the instantaneous frequency of the signal in the same time window. And the instantaneous frequency is it's a transformation you can make, and it gives you the characteristic frequency at each instant in the system. And so this is the mean in this time window, in the same 5-second time window around the SQ. About the moment, you ask how I define it. And the moment is, we simply define the plateau of the low frequency plateau. And by low frequencies is quite hard actually, because it dies off, it's very easily polluted by microseismic noise here. So we use between 1 and 2 hertz, and we got the value from that. So it's a crude, coarse estimation, and maybe there are a lot of problems with that. Okay. And we go.
Well, this presentation, I have a lot of questions about the others. There are questions that I had, like your model reminds me of the damage models that we use.
I'm sorry, can you speak up?
Of the damage models that are using like solid mechanics, like have you ever heard of the fiber bundle model?
I'm sorry, I can't hear you very much.
Like the fiber bundle model?
No.
Or lattice model?
No.
Basically, they're like systems where you have availabilities, and you load the system until the weakest point breaks, and this properties as the factor around the system. And for example, they recover the noise load, even when they use like the electric analogy for a lattice. And my question was that if you had any comparison between your formulation and those formulations, if
I don't.
anything would be. I worked a bit on that, and that's why I was.
Okay. I don't really. I think there might be a way to formalize how, or to simplify how valves interact, for instance, near those critical values, because we seem to get very similar migration rates near the for different valve distributions of these different with the same the same nominal distribution, but different realization of this valve distribution. We get very similar migrations near the critical fluxes. So there might be a way to formalize that in that way in order to do that, but I haven't done it, and I haven't really looked at the characteristic like Omori decay, for instance. It might be hard also because I don't know how I would do it because of there's no information about magnitude in there. So they're like the foreshock and the decay of activity after a main event. Yeah, but
There's the 2016 paper that we did that looked at the clustering just in time. So there's no repeat space. And that was the inspiration of actually the time last one. I find it's fascinating there. This is that all they think about like breaking rocks and things. But you know, they thought of really good ways you probably know some of them and to quantify the amount of clustering you have, the distribution of stress across these rods, and how they redistribute when one breaks. And so we did something where we looked at just the event count time series, and you look at the data correlation, you can compute the Fourier spectrum. If it's plus on, there's no clustering, and it's flat. But a very strong clustering will get up a slope. A slope parallelogram with Fourier spectrum. And so when you do that on LNP, you see exactly like a fiber rod bundle. Then the bigger question, like Gaspard was saying, is how do you bring in magnitude, or how do you bring in space? And that becomes a little more complicated. But there was a recent paper, there's a paper we did with Olivier Longuillet in 2017 that looked at just in time. And then recently there was David Crustal and Gaspard who looked at in time and space. It's basically the generic clustering you get between LNPs. And they didn't go and link it back to the fiber rod bundle per se. You can. I mean, it's just like one extra step. But you definitely see like it. That's as you see what's just like. And also, what we can do with the help as well. Just looking at the power question.
So can we that? Have we tried to compare the kind of clustering that you get in the time series, time series of event count?
Yeah.
Compared to US catalog, for example?
Yeah, I have. I assume the values were not very easy to compare. Maybe that's wrong, because of the way you would fit and you would try to fit to have this clustering exponent. But what we find is that closer to the critical fluxes, you get extremely clustered system. However, the closest you get, the more periodic behavior you get. And so the clustering exponent is gonna fall off a bit. And in the center, the time series so the event counting series, which is actually just a rate time series, can be sometimes picked as a Poisson process by a chi-square test or by the with the same exponent or looking at it. It looks like a Poisson time series, but when you look at exactly what's happening in the details, it's extremely clustered, just on a much shorter time scale. And so there's a lot of activity, not shorter time and space scale. So there's less coherence and synchronization than in those cases where it's closer to the critical fluxes.
Maybe we will trying to really get something comparable to the real capital modes, because and you have unlimited fractions, and I would think that it gives you something very different from, let's say, frictional objects where interactions are in all possible directions.
It might, yeah. Right.
My question is really a follow-up on that. You're describing the system as a pipe. Both of the monad thing. So the probability bearers you have are essentially infinitely long, a long strike.
Yeah.
And in reality, I would imagine if a cloud had a finite length of strike, then fluids would tend to go around it. So I was wondering if you thought about how this model would behave if you were doing it on the planes.
Yes, but it will be a bit of a non-answer, perhaps. But we made the approximation that actually it could be a network of pipes that can be connected in different places. And so you could have this kind of behavior in small sections of the pipes. That's the 1.5D model. And as soon as you get to 2D, this valve mechanism is harder to think of. You would have to have asperities that's very, I mean, perhaps lower diffusivity because you don't really stop the flux with just a system. Yeah, we can think of, I don't know, the one of the justifications for having a 1D system is also the patterns of striation that we see sometimes so when you don't look at time, you just look at the location of LFEs, there are sometimes patterns of striations. And so we would think of this kind of pattern as being symptoms of a particular permeable structure. But yeah, 2D is I think this kind of model is not extremely. They would have we would have to think of how the valve mechanism would work. I don't have an answer.
I would like to ask people from Zoom, if you have any questions, please unmute yourself and ask questions. Do we have any questions from Zoom? If we don't have any question, I think you will have the last question.
Oh, no. Yeah,
it's okay.
okay.
Okay. Cool. Thank you very much, Gaspard.